Welcome to my presentation about economics of sustainable hydrogen fuels for trucking, shipping, and aviation. I'm very happy about the opportunity to present you the results of our latest working paper from me, Jonas Martin, and Anne Neumann from the Norwegian University of Science and Technology, as well as Anders Odegaard from the research center SINTEF. We are part of Norway's leading research project, Zero Emission Energy Systems, to decarbonize the mobility sector, called FME MOSIS. In the center of our work is the question, which cost has decarbonized freight transport towards 2050 by using hydrogen fuels? And under hydrogen fuels, sustainable hydrogen fuels, we understand the use of pure hydrogen produced from renewable electricity and green e-ammonia as well as green e-fuel, so synthetic hydrocarbon. But not only the future costs are interesting, also the changes in competitiveness of trucking, shipping, and aviation while decarbonizing towards 2050. Therefore, we investigated 3 user cases. First, a long-haul truck, a 40-ton semi-truck with a payload capacity of 25 tons. A short sea vessel with a payload capacity of approximately 10,000 tons. And a short to mid-haul plane, here an Airbus A320 freighter with a payload capacity of 20 tons. If we only compare the fuel consumption for all 3 examples, then we see that the aviation sector, the plane, consumes much more fuel per ton kilometer compared to trucking and shipping. If we now include cost-intensive alternative fuels in the market, we directly see that all the 3 transport modes are impacted in very different ways. To bring sustainable hydrogen fuels into the transport markets, we looked at 3 different fuels: e-hydrogen, e-fuel, and e-ammonia. And we also specified the way of consuming them. For e-hydrogen, we assumed the use of fuel cells in the shipping and trucking sector and the use of adjusted jet engines for the aviation sector. For e-fuel, we looked at common engine technology, and for e-ammonia, we assumed the use of fuel cells in the shipping sector. To compare all these fuels in the 3 transport modes, it is important to have equal assumptions. And therefore, we decided to create a dynamic cost model from 2020 to 2050 and to include all costs of every needed process step in the value chain. So we started with the cost calculation for producing electricity for onshore and offshore wind power as well as hydropower, then calculated the future costs of electrolyzers and buffer storage to produce hydrogen, the needed reactant for e-fuel carbon and for e-ammonia nitrogen, and then different synthesis and upgrading processes, the liquefaction and storage, and the distribution of the fuel to the place of consumption. And here we also included the refueling infrastructure, which is very special for each transport mode. The first part of our value chain could be used to calculate the levelized costs of fuel, and then with the knowledge of the future fuel costs, we could calculate the levelized cost of transport for each transport mode. Our model includes 140 techno-economic parameters, and a very important information: we excluded any governmental intervention by taxes or subsidies, so it's a pure technology-driven cost calculation. In the first step, we calculate the levelized costs of electricity for offshore and onshore wind power as well as hydropower for the years 2020 to 2050. We include all needed cost components and their reduction potentials based on intensive literature review. We apply our model to Norway, which is seen as pioneering country if it comes to green electricity. Already 97% of the electricity are based on renewable sources, and is also an early adopter country if it comes to decarbonizing transport. We could find 3 promising locations for cheap electricity, and here you can see the capex shares for each technology and also operational expenses, as well as an offshore grid if it comes to offshore wind power, a fee to connect the offshore park with the mainland. We also included the uncertainty in the literature if it comes to future cost values, which you can here see as error bars. In the second step, we calculate the levelized costs of the fuels hydrogen, ammonia, and e-fuel. And we separate the x-axis into the source of electricity, so offshore and onshore wind power as well as hydropower. So where does the electricity come from? And the years 2020, 2035, and 2050. On the left side, you see the levelized costs of hydrogen in cents per kilowatt hour. And yeah, it's obvious that electricity costs are the main driver for hydrogen costs. So it's very important to use a cheap electricity source such as hydropower. And you can see the cost reduction potential of all components in the production chains, so that there is a cost reduction potential for the total hydrogen costs of approximately 50% towards 2050. We also calculated the levelized costs of ammonia and the levelized costs of e-fuel. E-fuel costs are mainly driven by the CO2 costs. Here we used direct air capture, which is very cost intensive, and also the loss of energy efficiency during the production process. Please be aware of the y-axis. For e-fuel, the y-axis has another scale. So e-fuel is definitely the most expensive fuel if we compare all the 3 fuels. In step number 3, we now calculate the levelized cost of transport for trucking, shipping, and aviation. But here I just show you as an example the shipping case. We calculate the transport costs in euros per ton kilometer from the years 2020 to 2050, and we use the already calculated fuel costs from step number 2, here based on the onshore wind scenario. If we look at the year 2020, on the left side you see the fossil fuel case. So here a common short sea vessel based on heavy fuel oil. And we also show the cost values for the investment into the ship, but also maintenance costs, general expenses, or cargo handling. So all costs which are needed to carry out freight transport from A to B based on a total cost of ownership approach. In light gray, you see the fuel costs here, as I said, for heavy fuel oil. If we now want to decarbonize this ship with our e-fuel already calculated, we see a sharp increase in levelized costs of transport for the year 2020. For the year 2035, we already see a cost reduction for the e-fuel case due to lower fuel costs, and that hydrogen and ammonia-based shipping could enter the market. Here we have much higher investments in new fuel cell technology for the ship, but this case also benefits from cost reduction for the fuels in the year 2035. In the year 2050, we see further cost reduction potential, especially for hydrogen and ammonia if it comes to the ship capex, but again also a cost reduction for the fuels. With this slide, I would like to give you an overview about the results for all three transport modes. So the figure on the right side shows you the levelized cost of transport in euros per ton kilometer for the years 2020 to 2050. On the top, we see the transport costs for aviation, in the middle for trucking, and on the bottom for shipping. And what's very obvious is that each transport mode has a very characteristic cost level. In gray, you see the levelized cost of transport if we use today's fossil fuels. So for aviation, Jet A1 fuel, for trucking diesel, and for shipping heavy fuel oil. In green, you see the levelized cost of transport using e-fuel, in blue hydrogen, and in yellow ammonia. And the percentages show you the transport cost sensitivity. So how strongly each transport mode reacts if you switch from a fossil solution to an alternative solution. For example, for the shipping sector, which we already know now, in the year 2020, if we switch from heavy fuel oil to e-fuel, then we have a cost increase of plus 232%. Our key takeaways: in our work, we could find the optimal fuel choices for our applications. So they are hydrogen for trucking, e-ammonia and hydrogen for shipping, and e-fuel for aviation. The shipping sector reacts most if it comes to sustainable hydrogen fuels. So if you look at the transport cost sensitivity, you here see the highest values if you switch from a fossil fuel to an alternative. Among the transport modes, alternative fuels do not change the overall cost ranking, which means that shipping stays the cheapest and aviation the most expensive freight transport mode, although all three modes suffer from alternative fuels. The choice of electricity sources has significant impact on early transport decarbonization. I can't show it in this figure here, but of course we not only used fuels based on the onshore wind scenario, which I show you here, we also calculated the scenario for offshore wind and hydropower, and we could see that of course cheaper electricity leads to cheaper fuels and thus cheaper transport costs. Very interesting here is that e-fuel reacts most if it comes to a change in electricity costs due to the high losses in the production chain. And the last decarbonization pathways are out of reach without the use of economic instruments by 2050. So although we have a quite large cost reduction potential in every transport mode, we still have a cost gap between the fossil solution and the alternative solution. And here it's very important to implement economic incentives to stimulate the market, for example with taxes and subsidies. The last point brings me to a short outlook. In the next step of our work, we want to investigate the question where to allocate policy instruments to make sustainable hydrogen fuels economically competitive in heavy-duty transport. So due to our very detailed bottom-up approach, we can now look into every cost component in every box where it is most optimal to allocate subsidies or taxes. So is it better to support the electricity production, for example the windmill, to achieve low-cost electricity, or is it more efficient to spend public money on the consumer side to support the purchasing of new truck technology? And yeah, with this outlook, I thank you very much for your attention, and I'm very interested in your questions and comments. Thanks a lot.